Voyager 1's magnetic highway discovery. On December 3rd, 2012, NASA held a press briefing to announce something that sounded at first like a simple update on a decades-old mission. What they actually confirmed was considerably stranger. The protective magnetic bubble surrounding our entire solar system, the one that's supposed to shield every planet from the harshest radiation the galaxy has to offer, wasn't sealed. Voyager 1 had found a direct connection, a kind of open channel linking the inside of that bubble straight through to interstellar space itself, letting particles flow freely in both directions. Scientists gave it a deceptively casual name, the magnetic highway. Picture the animations NASA eventually released to explain it. Clouds of pink particles representing charged material native to our own solar system, suddenly streaming outward in a clean, unified direction, while a wave of blue particles, cosmic rays born in explosions, light years away, poured inward to take their place, the entire scene playing out like a time lapse of a border crossing nobody had realized was open. This is the story of the crack Voyager 1 found at the edge of our solar system, what it actually means for the shield protecting Earth, and why its twin spacecraft, traveling the exact same journey years later, never found the same opening at all. To understand why this discovery mattered, you first need to picture what the edge of the solar system was expected to look like before Voyager 1 actually got there. The sun constantly blows out a stream of charged particles called the solar wind in every direction, inflating an enormous bubble around the entire solar system known as the Heliosphere. That bubble acts as a genuine physical shield, deflecting a significant portion of the dangerous, high-energy cosmic rays that stream in from exploded stars and other violent events happening elsewhere in the galaxy. Scientists expected the outer edge of that bubble, the boundary where the sun's influence finally gives way to true interstellar space, to behave something like the surface of a tightly inflated balloon, a fairly clean, gradual transition from one environment to the other. What Voyager 1 actually found, starting in the summer of 2012, looked nothing like that simple picture. Launched in September of 1977, Voyager 1 had already spent 35 years traveling outward. By the time it reached this stretch of its journey, sweeping past Jupiter and Saturn in its first few years before angling upward, out of the plane the planets orbit in, on a trajectory aimed squarely at the edge of everything the sun's influence could reach, carrying a small gold-plated phonograph record and a set of scientific instruments that had already vastly outlived their original mission planners' expectations. By 2012, the spacecraft was roughly 11 billion miles from Earth, so far out that a radio signal traveling at the speed of light needed 17 hours just to make the one-way trip back home, a distance so vast that every single command sent from mission control and every reading sent back had already spent most of a full day in transit before anyone on either end could act on it. At that almost incomprehensible distance, Voyager's instruments began recording something genuinely new, a region unlike anything the mission had encountered in its previous 3.5 decades of continuous operation. Voyager 1 carries 2 separate instruments capable of measuring charged particles, and starting on July 28, 2012, both of them picked up a dramatic, sudden shift in the environment surrounding the spacecraft. Picture the difference the way NASA's own visualizations eventually described it. Before reaching this new region, charged particles around Voyager behaved chaotically, bouncing around in essentially random directions, trapped and jostled inside the heliosphere the way traffic gets stuck weaving through side streets and local roads inside a city, unable to move in any single consistent direction for long. Then, abruptly, that changed. Lower energy particles that originated from inside the solar system's own bubble suddenly began zipping away in a clear, consistent direction, escaping outward far more efficiently than before. At the very same time, higher energy particles from far outside the solar system, cosmic rays that had been struggling to penetrate the heliosphere's defenses at all, started streaming inward with dramatically increased ease. It was as if a fast, wide, perfectly straight highway had suddenly opened up, connecting 2 previously separated road networks, letting traffic flow rapidly in both directions, where before it had only crawled. The physical explanation behind that shift turned out to be exactly as significant as the traffic metaphor suggests. In this specific region, the sun's own magnetic field lines were directly connecting to interstellar magnetic field lines, essentially fusing 2 separate magnetic systems into a single continuous pathway. Rather than the heliosphere's boundary acting as a closed, self-contained barrier, keeping the sun's magnetic environment cleanly separate from the galaxies, Voyager had found a specific, localized breach, a genuine structural opening, where the 2 systems linked up directly, letting particles cross freely along that connected field, rather than being blocked or deflected the way a fully sealed boundary would require. Stimatios Crimigis, the principal investigator on Voyager's low-energy charged particle instrument at Johns Hopkins Applied Physics Laboratory, described just how convincing the shift looked from inside the data alone. if he were judging purely by the charged particle. Readings, he said, he would have concluded Voyager had already left the heliosphere entirely and reached true interstellar space. That statement is worth sitting with, because it captures exactly how disorienting this discovery actually was for the scientists living through it in real time. One entire category of evidence, the charged particle data, was screaming that Voyager had already crossed some fundamental threshold. But a second, equally important measurement told a completely different story. Voyager's magnetometer. The instrument tracking the actual direction the surrounding magnetic field was pointing showed no change at all. Scientists had a specific, well-reasoned prediction for what should happen at the true boundary of the solar system. The magnetic field's direction should visibly shift once Voyager finally crossed into a region governed by the galaxy's own magnetic field rather than the sun's, the cosmic equivalent of a compass needle swinging to point anew, way the moment you cross from one country's magnetic influence into another's. That shift simply wasn't happening, even as the particle data behaved as though the spacecraft had already left. The magnetic highway, in other words, produced two contradictory seeming signals at once. One instrument suggesting Voyager had already crossed over, another insisting it hadn't, an internal disagreement within the data itself that took real scientific patience to sort through properly rather than announce prematurely exactly the kind of methodical caution that separates a confirmed discovery from a premature headline. The region itself didn't even behave consistently once Voyager first found it. According to the mission's own tracking, Voyager first entered the magnetic highway on that same date in late July 2012, only to have the region ebb and flow around the spacecraft repeatedly over roughly the following month, the connection appearing to open and close multiple times before Voyager entered it again on August 25th, and the environment finally stabilized a stretch of weeks during which the spacecraft essentially crossed back and forth over the same threshold several times before finally settling on one side of it for good. Each time the spacecraft passed back into the highway, the strength of the surrounding magnetic field grew noticeably stronger, even though its direction stayed the same throughout, a genuinely strange combination that suggested Voyager was approaching something significant without yet fully arriving at it, gathering intensity the way pressure builds ahead of a storm front without the front itself having actually broken yet. Ed Stone, the mission's longtime chief scientist, told reporters at the time that the team genuinely didn't know how much further Voyager had left to travel before crossing into true interstellar space, estimating it could be anywhere from a few months away to several more years, an honest admission of uncertainty about exactly how close the spacecraft actually was to the finish line of its original planetary mission's next great milestone. As it turned out, the wait wasn't nearly as long as the more cautious estimates suggested. Voyager 1's actual crossing into interstellar space, confirmed through a combination of instruments including a fortuitous burst of solar activity that let scientists calculate the true density of the surrounding plasma, came within roughly a year, placing the historic transition on August 25, 2012, technically the same date the magnetic highway region had most recently, stabilized around the spacecraft. That timing makes clear, in retrospect, exactly what the magnetic highway actually represented. Not a bizarre, disconnected anomaly, but the final transitional layer of the heliosphere itself, a genuine seam where the sun's magnetic domain begins directly fusing with the galaxies before giving way entirely, the last structural feature Voyager passed through before formally becoming the first human-made object to leave the solar system. Here's where the story gets genuinely more complicated and considerably more interesting, because Voyager wasn't traveling alone. Its twin, Voyager 2, launched just weeks earlier in 1977, but following an entirely different trajectory, one that eventually took it past Uranus and Neptune as well, was also approaching its own eventual crossing into interstellar space, though along a completely different section of the heliosphere's outer surface. When Voyager 2 finally made its own crossing, in November of 2018, 6 years after its twin, scientists watched closely for any sign of a comparable magnetic highway. The same dramatic, sudden connection between solar and interstellar magnetic field lines that had defined Voyager 1's final approach. It never appeared. Voyager 2's transition showed genuinely similar broad patterns to what its twin had experienced, but the changes arrived far more gradually, without the same sharp, highway-like connection abruptly opening up and stabilizing the way Voyager 1's data had shown. Scientists studying the comparison have been explicit that they don't believe Voyager 2 ever passed through an equivalent magnetic highway region at all. That asymmetry matters enormously for how researchers now understand the true structure of the heliosphere's outer edge. If the magnetic highway had shown up identically for both spacecraft, it would have suggested a uniform, predictable feature present everywhere along the boundary, a kind of standard architectural element built into the heliosphere's entire outer surface, the same way a sealed door works identically, no matter which side of a building you approach it from. Instead, its presence at one crossing point and apparent absence at another, sampled years apart and at a completely different location along the boundary, suggests something considerably messier. A boundary whose exact structure varies meaningfully depending on exactly where and exactly when a spacecraft happens to pass through it, shaped by local conditions in the surrounding interstellar medium and the sun's own fluctuating activity, rather than existing as some fixed, permanent architectural feature stamped uniformly around the entire bubble. Researchers have compared the resulting picture to a coastline rather than a smooth balloon surface, uneven, irregular, and shaped differently depending on exactly where along its length you happen to be standing when you finally reach it. That variability carries real, practical weight beyond simple scientific curiosity, because the heliosphere's core function is defensive. It exists to deflect a meaningful portion of the dangerous, high-energy cosmic radiation constantly streaming in from the wider galaxy. Radiation produced by exploding stars and other violent events scattered across the Milky Way. Radiation that would otherwise reach Earth and the rest of the inner solar system in much higher doses. A boundary that behaves like a uniformly sealed barrier everywhere provides one kind of protection, consistent and predictable, regardless of location, the sort of shield you could model, with a single, simple equation. A boundary that occasionally opens direct, highway-like channels connecting straight through to interstellar space, channels that appear to come and go depending on local, possibly time-variable conditions, suggests the shield's actual effectiveness may fluctuate considerably more than a simple, static model would predict, with real consequences for how confidently scientists can forecast radiation exposure for any future spacecraft or any future human mission that might eventually need to travel through this same outer region of the solar system, decades or centuries from now, long after both Voyagers have gone silent for good. More recent research building on both Voyager's full journeys through this outer boundary has only reinforced the picture of a considerably more complicated, layered structure than early pre-Voyager models ever anticipated. Scientists studying Voyager 2's own 2018 crossing, using its still-functioning plasma instrument, an advantage Voyager 1 no longer had by that point since its equivalent instrument had failed decades earlier, later identified a distinct, thin magnetic barrier sitting right at the heliopause itself, a separate, more concentrated layer of intensified magnetic field wedged between the heliosphere and true interstellar space, strong enough to noticeably influence which cosmic rays are allowed to leak through and which get deflected away entirely. Essentially, a second, independently discovered structural feature layered on top of everything Voyager 1 had already revealed about its own, differently structured crossing point years earlier. Combined with Voyager 1's earlier magnetic highway, the overall picture that's emerged across both spacecraft's full journeys describes an outer boundary built from multiple distinct layers and features, rather than a single, simple wall, each one apparently capable of appearing, strengthening, weakening, or vanishing, entirely depending on factors researchers are still working to fully map out, using nothing but 2 aging spacecrafts' worth of direct, hard-won measurements gathered years and billions of miles apart. It's worth being clear about what all of this does and doesn't actually mean for anyone living on Earth right now. None of these findings suggest any kind of imminent danger, a sudden flood of radiation, or any acute change to conditions inside the solar system today. The heliosphere continues functioning as an effective, meaningful shield overall, exactly as it always has, and nothing about the magnetic highway discovery changes the radiation environment anyone on Earth or in near-Earth orbit actually experiences day to day. What's changed is scientists' confidence in describing that shield as a simple, uniform, predictable structure that behaves identically no matter where or when you happen to study it. Voyager 1 found a genuine crack, a real physically confirmed channel where the boundary's usual defenses briefly gave way to a direct connection with the wider galaxy, and its twin, traveling the same fundamental journey along a different path, found something considerably more gradual instead. That difference is exactly the kind of detail that only becomes visible when you send not one, but 2 independent spacecraft on the same historic crossing, sampling different points along a boundary nobody had ever directly measured before. Either probe got there. A reminder that even our most fundamental assumptions about the shape of our own cosmic neighborhood sometimes only get corrected once someone actually goes out and checks twice. So here's where that leaves things today. The magnetic highway Voyager 1 discovered back in 2012 remains one of the clearest, most direct pieces of evidence that the boundary protecting our entire solar system isn't the smooth, sealed bubble earlier generations of scientists assumed it would be. It's a structure with genuine openings, temporary connections, and layered defenses that vary from place to place and possibly from moment to moment, mapped in real detail for the first time, only because 2 aging, half-century-old spacecraft happened to be traveling through it on 2 different paths at 2 different times, willing to report back exactly what they found, rather than what anyone expected them to find. Think about how differently this entire story could have been told if only one spacecraft had ever made this journey. If Voyager 1 alone had reached interstellar space, the magnetic highway would likely have been written into the textbooks as a standard, expected feature of the heliosphere's boundary everywhere, a permanent architectural fact about how the solar system's edge works. It took a second spacecraft, arriving 6 years later along an entirely different path, to reveal that the highway wasn't a universal rule at all, but a specific local feature tied to conditions that clearly aren't identical everywhere along the boundary. That's the quiet, underappreciated value of having sent 2 Voyagers rather than 1, a redundancy nobody originally justified purely on the grounds of scientific completeness that ended up rewriting the entire understanding of one of the most fundamental structures protecting our solar system. Somewhere, billions of miles from Earth, right now, both Voyagers continue moving outward through interstellar space, still transmitting. Whatever new structural surprises the true edge of our solar system has left to reveal, on a mission that was never supposed to last long enough to answer questions nobody had even thought to ask when it first launched. Their power keeps fading, a little more every year, and the day is coming, likely within the next few years, when the last instrument on each spacecraft finally goes dark for good. Until then, every signal that makes the long journey back to Earth carries the possibility of one more crack, one more seam, one more piece of evidence that the shield surrounding everything we call home was never quite as simple or as solid as anyone assumed before 2 stubborn aging machines actually went out and checked for themselves.